Hi, everyone. Happy to see you all. Today, Mitchell Taylor from UC Berkeley speaking on stable phase retrieval in function spaces. Mitchell?
All right. Well, thank you very much for the introduction and for inviting Dan and I to speak on this. So today will be, I guess, part two of the talk that Dan started last week. It'll continue on stable phase retrieval, and it will continue on this joint work with Dan, Timur, and Ben. But I'll also mention a separate work with Mike Christ and Ben Pinot. So maybe we can get started. So just to be clear on notation, throughout the talk, omega mu will be a measure space, usually a probability space, and P will be between 1 and infinity, but mostly finite. And C will denote some uniform constant. And the absolute value function is well the absolute value function, not the norm. So I will use the notation of 1 bar around f to denote the absolute value function. And the most important remark is that the scalar field in this talk may be real or complex. That's subject to change depending on the results, and it makes a huge difference in this direction of research. So if it's unclear at any point what the scalar field is, just let me know. All right, so this is the inequality that we're going to be looking at, and it's a bit of a funny inequality, but let me try and give you some intuition for it. So we're going to be interested in subspaces of LP, or general Banach lattices maybe, but usually LP, where you can essentially recover the absolute the function from its absolute value. So these are going to be rather small subspaces. They'll be a bit rare, but we'll show that they're actually quite plentiful and have some interesting properties. Okay. So the definition here is a subspace E of LP is said to do C-stable phase retrieval if whenever I take two functions in the subspace, I have a certain inequality being valid. And this inequality tells me, well, if the absolute value of f is close to the absolute value of g, then necessarily f has to be close to a unimodular multiple of g. Okay. So to make notation clear, this inf on the left-hand side, in the complex case, it's running over all elements of the unit circle, right? So it's lambda can be any scalar of the form e to the I theta, where theta is real. But in the case of real scalars, so real valued functions, this inf is just a 2-point inf, because the only unimodular scalars are plus and minus 1. And so this inf reduces to just the minimum between the norm of f minus g and the norm of f plus g. And the fact that in the real case, you only have 2 ambiguities, where as in the complex case, you have a whole circle of ambiguities, is what makes the complex case a lot more difficult. All right, and to get a flavor of this inequality, let's look at the simplest case. So let's look at the case where I take f and g in my subspace and assume that they have the same absolute value. Okay. And if I make this assumption, then, well, this inequality tells me that since the right-hand side is 0, the left-hand side must be 0 as well. And from that, I deduce that f is necessarily a multiple of g. And this type of implication is known as phase retrieval, because all you have access to is the magnitude of f. And then within this subspace, the magnitude of f determines the function up to the unavoidable ambiguity of, if you have a subspace, I can multiply by scalars, and unimodular scalars won't change the absolute value of a function, right? So phase retrieval is the study of recovering phases up to like a global parameter that's usually unavoidable. Okay. So in a slightly different language, phase retrieval requires that this map defined on E that sends the absolute value of f back to f modulo global phase be be well defined, right? So that that's what this implication says. But this inequality here is a lot stronger. It says that not only is this map well defined, it's also Lipschitz continuous with this with this constancy here. Okay, so not only is phase retrieval possible, it's stable in a nice way. All right. So where do problems in phase retrieval arise? Well, they arise in several applications, and Dan mentioned frame theory as his, I guess, source of motivation, because, well, he came from doing some work in frames. Since I have maybe a little bit more of a harmonic background, one application I like is Fourier phase retrieval, and it actually is better for our paper, so as I'll explain in a moment. So what's the goal of Fourier phase retrieval? Well, it turns out that in many physical experiments, when you take some measurements, you're not able to directly measure the signal f that you're ultimately interested in. What the detector picks up is the magnitude of the Fourier transform of f. Okay, so this is so in certain optical and crystallography applications, this is what experiment detects. But of course, you need to recover your original function back to understand what's going on. And so the goal in Fourier phase retrieval is to recover a function f from the magnitude of its Fourier transform. And since any type of experiment will involve error, you also want some stability of this recovery. So you're going to want an inequality of this form that says, well, not only can I recover f from the magnitude of f hat, which would be which this inequality would imply, right? Because it says that whenever the magnitude of f hat is the magnitude of g hat, f is necessarily a multiple of g. But it says you can do it stably. So if the magnitude of a Fourier transform of some signal is close to the magnitude of the Fourier transform of other signal, then necessarily these two signals are very close up to a phase. So this would be this inequality that would state that the recovery of f from the magnitude of the Fourier transform of f is stable. And the question of where should this inequality be true? Well, it should be true whenever I take f and g in a certain subspace E of L2, which incorporates whatever additional constraints I know my signal will satisfy, right? Because obviously an inequality like this cannot be true on all of L2. That's you can't recover a function from the magnitude of the Fourier transform, but on sufficiently small subspaces you can, and in experiments, of course, you're not going to be interested in every possible signal. You're going to a priori know some constraints, some linear constraints on what your function must look like. So this is what inequality you would like. And I'll point out here that this inequality doesn't exactly look like the one on the previous slide, because I have Fourier transforms on the right-hand side, but not on the left-hand side. So luckily, we all know Plancherel's theorem, which says that I can, put Fourier transform wherever I want in L2. So what I'll do is put hats on the left-hand side, so the hats match the right-hand side, and I'll change my notation. I'll define f to be capital F hat and g to be capital G hat. And what I learned from this little exercise is that a subspace E of L2 does Fourier phase retrieval, meaning that you can recover the function from the magnitude of its Fourier transform, if and only if, well, the Fourier transform of that subspace, when I view it in L2 in, I guess, frequency space, does phase retrieval in the sense of the first slide. Okay, and the point here is that this inequality here involved this operator here, and the previous inequality was just about subspaces of L2, and we want to somehow remove the operator and just study subspaces of L2 with this recovery property, and then see where we can go from there. Okay. All right, so as I was mentioning, in Fourier phase retrieval, you try and recover a function f from the magnitude of the Fourier transform of f. But there are many other physical scenarios where the Fourier transform is not the relevant operator, but as Dan was saying, the relevant operator is usually, let's say, analysis operator of a frame. So maybe the Gabor transform or something like this, or generally speaking, what you want to do is you want to consider some transform from a Hilbert space to L2 and recover f from the magnitude of TF, right? So I was mentioning the Fourier transform as an example for T, and Dan mentioned the analysis operator of a frame as an example for T. And the point here is that all of the examples I know of phase retrieval can be rewritten in the language of subspaces of L2 by just the fact that the recovery of f from modulus of TF is possible and stable if and only if a certain subspace of L2 satisfies our inequality on the first slide, and that subspace is the one determined by embedding the Hilbert space into L2. Okay. The logic is exactly the same as the logic with the Fourier transform, but the point here is that somehow the physics determines what operator you're interested in, and the operator determines which subspace of L2 you want to do stable phase retrieval on. And we were just looking at the question of, well, which subspaces of L2 in general do phase retrieval? Because as you'll see, as Dan was mentioning, frames can never do stable phase retrieval. So I mean, in infinite dimensions, that's impossible. So the question of just building these subspaces is non-trivial. But as we'll see, the reason I like Fourier phase retrieval is because it is possible to do it stably. So we'll actually build the first examples of subspaces that do stable Fourier phase retrieval and are also infinite dimensional. All right, so that's maybe one motivation for this talk. There's other ways to motivate phase retrieval, for example, through the Pauli problem in quantum mechanics. But if you're interested in that, you can just take a quick look at the introduction of our paper, just for time constraints. So what I want to do instead is talk about Dan's talk, just briefly go over what he discussed, and in particular talk about the kind of enemies that you deal with when you want to prove a subspace as phase retrieval. Okay, so the first obstruction to phase retrieval, Dan already mentioned, it's very simple, is, well, if I take two elements of my subspace of LP and I assume that these functions are disjointly supported, then I'm going to have a lot of troubles. And the reason is, well, I look at a graph like this. I look at two functions, f and g. So maybe the blue one is f and the red one is g. And let's say these two functions lie in my subspace. Well, then the sum of the functions lies in the subspace and the difference of the functions lies in the subspace. And I think we all agree that these will have the same magnitude, right? Because, I mean, it's just flipping around the x-axis. But the problem is, if I look at f plus g, I see the graph kind of as pictured, but when I look at f minus g, this right-hand side flips. And although f plus g and f minus g have the same modulus, they're not multiples of each other, right? So the magnitude of the functions in my subspace does not determine the functions up to global phase, because I was allowed to just switch the sign on a portion of my measure space, but not the other. Okay, so this is the kind of obvious obstruction to phase retrieval, and the obvious obstruction to stable phase retrieval as well. This same obstruction, except, well, I can allow a little bit of overlap, right? Because if I have a little bit of overlap, this argument essentially goes through in the norm topology. Okay, so the statement here is that, well, if I take a subspace of LP and it does stable phase retrieval, then it certainly cannot contain almost disjoint pairs. And to be clear, what do I mean by almost disjoint pairs? Well, I first off mean, I'll say that a subspace contains almost disjoint pairs if for any epsilon bigger than 0, I can pick two functions f and g in the sphere of E, where, well, their pairwise inf is maybe not 0, which would be the case. This would characterize them being disjoint, but it's almost 0, so it's less than epsilon. Okay. And I just want to introduce this because I'm going to use the language of almost disjoint pairs and almost disjoint sequences. But when I use this language, I'm always assuming that the functions I start with are normalized. Because, I mean, obviously, if f and g were 0, this would be true. But what I want is two functions that lie in the sphere whose pairwise inf becomes very small. All right, so that's the very obvious obstruction to stable phase retrieval, and the first theorem that Dan, Timur, and Ben and I were able to prove is that when you're considering real scalars, this is the only obstruction to stable phase retrieval, and this is not only true just in LP spaces; it's true for general Banach lattices. So the theorem we were able to prove is that a subspace E of a real Banach lattice does stable phase retrieval if and only if the subspace does not contain almost disjoint pairs. Okay. So for real scalars, this is the only obstruction. For complex scalars, there's a whole lot more obstructions, as I will get to later in the talk. But this is the theorem that kind of motivated the questions we asked and the sorts of techniques we use to answer these questions. All right, and I can state this very precisely. Stable phase retrieval in the real case is about not having disjoint vectors in your span. And I guess very lucky for us, coming from Banach lattice theory, the study of subspaces lacking almost disjoint sequences is very classical. I'll again remind you what an almost disjoint sequence is, just because, again, I'm omitting the word normalized when I shouldn't. So I'll say a sequence Fn is an almost disjoint sequence if, first of all, it's normalized, and I can find disjointly supported functions Dn, where Fn minus Dn converges to 0, meaning that Fn asymptotically behaves like this disjoint sequence. Okay. And well, when I say this is classically studied, there must be some theorems on it, or that wouldn't be true. And the theorem that is most important to us is a theorem about LP of a probability measure with finite P, and it says that a closed subspace E of LP satisfies several equivalent properties. The first being lacking almost disjoint sequences, which is the one we're interested in. But importantly, this is equivalent to the LQ norm being equivalent to the LP norm on this subspace for every choice of Q less than P, and also just for one choice of Q less than P. Okay. So the subspaces that do not contain almost disjoint sequences have the property that whenever I take an LQ norm where Q is less than P, these will be equivalent on that subspace. Okay. So since this property is going to be relevant to us, let's give it a name. I chose just to call it property star, and this property depends on P because we're interested in the subspace of LP, and I get equivalence with all LQ norms when Q's less than P. So P is very relevant here. And well, what do I learn from this discussion? Well, I learned that stable phase retrieval in LP implies lacking almost disjoint pairs. And so if I lack almost disjoint pairs, I certainly lack almost disjoint sequences, right? So this implication is clear. And then from the fact that in 2 I have for all Q less than P, and in 3 I have there exists Q less than P, it's also clear that if I satisfy this star property in LP, then I satisfy it in LQ as long as Q is less than P. Okay. So this is the main implication I want to point out. And as a corollary of this implication, I know that if E is a subspace of LP, which does stable phase retrieval, then I may view it legitimately as a subspace of LQ for any Q less than or equal to P, because all the LQ norms are equivalent to the LP norms, right? And so, a natural question that Dan asked in the last talk is, well, we have this implication here that no normalized almost disjoint sequence in LP implies no normalized almost disjoint sequence in LQ. Is the same fact true for SPR? So is it true that if I lack almost disjoint pairs in LP, that I also lack almost disjoint pairs in LQ? Okay, so that's the question Dan mentioned, and he gave our result on this, and the result is, well, it depends on what side of 2 you're on. So our theorem was that if P is bigger than or equal to 2, then I can find subspaces of LP that do SPR in LP, but when I view them in LQ, which I can do because the norms are all equivalent, they'll fail to do stable phase retrieval in that LQ topology for any Q less than P, right? And this is because the right-hand side of the inequality is modulus of F minus modulus of G, and that does not lie in the subspace, right? So although the norms are equivalent on the subspace, meaning that the left-hand side of the SPR inequality doesn't depend on whether you're a Q or P, the right-hand side does. And of course, this is what causes this phenomenon. But when P is less than 2, this doesn't happen. So when P is less than 2, and I take any subspace of LP that does stable phase retrieval, then it will also do stable phase retrieval when viewed inside of LQ for any Q less than or equal to P. All right, so I think that's everything I wanted to say about Dan's talk, and the reason I wanted to go back to this is because this dichotomy I hope to explain and elucidate with some of the results in this talk, at least on a very heuristic level. I'm not going to go into the proofs of these things, but on a very heuristic level, I want to tell you why P equals 2 is important here. But I have lots to do before then. So I want to first tell you about examples of subspaces of LP and some of the other that do SPR and some other connections we were able to make. All right, so so far in the talk, I just did some recap and tried to motivate why phase retrieval is relevant in various physical scenarios, but there's something I haven't done, and I don't think, well, Dan might have stated this, but he also didn't do this, is he didn't give a single example, right? We haven't actually given you any real, well, okay, we did formally in the proof of the last theorem, but I want to give you some more examples, and the big problem in this area is that, well, no examples were known at all. So in particular, no infinite dimensional subspaces of L2 were known to do stable phase retrieval, at least until last year. Okay, so last year is when the study of infinite dimensional stability was first shown to be possible. The study of finite dimensional subspaces doing stable phase retrieval is very well studied, and there are many very interesting results in that direction. But I won't comment on those too much. But the problem of infinite dimensional subspaces doing SPR was generally believed to be not possible. And the reason is because, well, if you use the analysis operator of a frame, then it definitely is impossible, right? So the reason this is impossible for a discrete frame should be more clear to Banach space people, because a discrete frame maps you into little L2. And I guess everyone in Banach space knows the gliding hump argument. So if you take a subspace, an infinite dimensional subspace little L2, then you can push a gliding hump and create almost disjoint vectors, right? So it's if you know this, then the instabilities are inherent because you're working with little L2 instead of capital L2. But even for continuous frames, it's been shown that stable phase retrieval is impossible. And this is, well, one of the reasons why the problems in infinite dimensions weren't studied. But as I'll try and convince you, if you replace the analysis operated frame by the Fourier transform, then not only is this physically relevant in some situations, but it's completely possible to do stable phase retrieval. Okay, and this until last year remark was because of a very interesting work of Calderbank, Domichis, and the two Freemans. So I always joke this is not a typo. This is both Dan and Nikki. So they were able to construct the first infinite dimensional subspaces of L2, but I'll critically note here over the real field. Okay, so their examples work when you consider real valued L2, but they won't work when you consider complex valued L2. Okay, so what I want to do now is just give you some extremely simple examples of subspaces that do stable phase retrieval, and I chose these examples because they are so simple. We can say more. So these examples for us were motivated by the theory of lambda p sets, and there's a big theory here about densities and stuff like this, and we were able to construct subspaces of somehow maximal density that do stable phase retrieval, but for the sake of clarity, I'll omit these and just give you the simplest examples of subspaces we can build. And the simplest example that works is, well, let's consider L2 of the unit interval. Let's consider the function sine of 2 pi 4 to the nx, where n runs through n. Let's take the closed subspace generated by this set, and this subspace will do stable phase retrieval. So with this, I can just say that, you know, subspaces doing stable phase retrieval, although they are quite rare, they're not completely pathological. They, I mean, you can build these in somehow elementary ways. And another example we have using IID vectors is if you take any probability measure mu, and you take a sequence of mean zero IID random variables in L4, then they will actually do stable phase retrieval if and only if the trivial condition is satisfied. So if I started with a function with absolute value identically constant, I make an IID sequence out of it, the absolute value would then still be constant for all choices of n, and then clearly the magnitude of the function wouldn't determine the function. But this is the only obstruction when working with IID variables. So the theorem says that I take any mean zero IIDs, as long as that sequence is not identically constant in modulus, the closed span of it will do stable phase retrieval. And I'll point out, I'm lying a bit because this is in L4, and stable phase retrieval will be deduced in L4 as well, not L2. And I'll explain why L2 is not the thing that appears here, and then I'll explain how you get to L2, but there's still some mysteries there that I don't understand. All right, so these are two, I think, very simple examples of subspaces that do stable phase retrieval, but I also want to point out that these subspaces only do stable phase retrieval over the real field. These will not do complex stable phase retrieval, and I can give you a very, very simple argument for why. Well, the reason why is that if I take any SPR subspace of L2, or really any Monoglottis, and I assume it does SPR in the complex case now, not the real case, then my claim is that this subspace cannot contain linearly independent real vectors. Okay, and how do I prove this? Well, I suppose I take two vectors f and g in my subspace. I assume they're real and they're linearly independent. I form the vector f plus ig, and I form the vector f minus ig. And since these functions f and g are real, the function f plus ig will have the same modulus as the function f minus ig, right? But f plus ig will not be a unimodular multiple of f minus ig because I chose f and g to be linearly independent, right? So this gives an example where this function here and this function here have exactly the same modulus, but they're not linearly dependent vectors, meaning that any subspace which contains two real vectors, or equivalently a function and its conjugate, that'll be an obstruction to complex phase retrieval. Okay. And if you look on the last slides, I mean, sine is clearly a real function. I assumed, I don't know if I stated it, but I was assuming I'm working with real valued functions here. And so these subspaces have no chance of doing stable phase retrieval in the complex field. Okay. So what does, and luckily we have very simple substitutes for these examples. So let's look at a trigonometric polynomial. Let's assume it's just an L2 of the unit interval, and it's given by a finite sum. It's just sum from k equals 1 to n of some coefficients times e to the 2 pi I kx. Okay. An obvious, well, okay, then my claim is that as long as the magnitude of p is not identically constant, then if I look at the closed span of sufficiently Lacunary dilates of this polynomial, then that will do stable phase retrieval in the complex sense. Okay. And of course, let me be clear here. So the assumption that absolute value of p is not constant is completely necessary, because if I take a function with constant absolute values and I build dilates of this function, it'll still have constant absolute value, and then the absolute value of the function wouldn't determine the function. That would mean I fail to do phase retrieval, right? Because phase retrieval is exactly the study of recovering a function from its magnitude. And the point here is that, well, this is actually the only obstruction to phase retrieval as long as your dilation set is sufficiently sparse. So we need the dilates to be at least 3 times the length of this this sum. And there's one key and very innocuous assumption in this theorem, and it's that this sum here starts at k equals 1. Okay, so if you look at this, you might think it's a contradiction to the last example, because I told you sine of 2 pi x and then dilating that function won't do stable phase retrieval. But that won't be an example of a polynomial of this form, because sine is formed from frequencies 1 and -1, right? So it's sine of 2 pi x is what? E to the 2 pi x minus e to the -2 pi x over 2i. So it's the case k equals 1 and -1. And it's this cancellation between positive and negative frequencies that makes sine a real valued function. And if I start this sum at 1 and don't include any negative frequencies, such a cancellation won't happen. Okay, so that's this. I mean, it looks like a nothing assumption, but it's extremely important that this sum starts at 1, and I'll try and explain why. Okay. So I want to give you a basic idea of the proof of this this theorem, and the idea is, well, I want to build a subspace of LP that does stable phase retrieval, and I should start by building a subspace by picking a good basis. And what I'm going to do is pick a nice orthonormal basis. Okay, so I'm going to consider a subspace of LP spanned by some very nice orthonormal sequence Rn. And this is legitimate, by the way, because when p is bigger than or equal to 2, I'll only consider the case p bigger than or equal to 2. And in that case, if I'm going to build a subspace doing stable phase retrieval, it has to be a Hilbert space. So I mean, this is, of course, backwards logic, but it's going to work out. And the idea here is, well, if I have a nice basis, then I can expand functions with respect to that basis. So I can take any f in my subspace and write it as a series in terms of a n Rn, right? And the point of phase retrieval is to recover the function from its absolute value. So what I want to do now is write a very nice expansion for the absolute value of the function, right? So what I want to do is take absolute value of f and again write it in terms of a sum of the basis functions. Okay. And then I'll compare the coefficients and work like this. And at this point, you might be just completely objecting, and the reason is because, well, this is not going to ever work, right? Because the absolute value of f won't even lie in the span of Rn in general, right? So although I can expand f in terms of a series in terms of Rn, there's no way I can generally write the absolute value of f in terms of this series as well, right? So this type of logic is doomed to fail, but at least formally speaking, the magnitude of f squared does have a nice expansion in terms of the basis, right? So I can obviously write absolute value of f squared as the sum over m and n of an bar, rn bar. Okay? And of course, this is not a sum with respect to Rn. I get products showing up here, but at least formally speaking, I do have a nice expansion for f squared. All right. And now what I want to do is just rearrange the sum to try and find out what are my enemies for phase retrieval. And my biggest enemy in phase retrieval, as you saw from the last slide, is when things have constant moduli. Okay, so first of all, let's say I normalize f to have norm 1, let's say, but anyways, or these Rn's are orthogonal, so or orthonormal. So you know, if the function is going to have constant moduli, it'll be moduli 1, say. So this is my main obstruction to phase retrieval, is when the magnitude of Rn squared is identically 1. So what I want to do is use this formal decomposition to avoid this obstruction. Okay. So what do I do? Okay, so I copy this on the next slide. The idea of this proof is, well, let's put on conditions onto these products that make this series here also an orthonormal expansion, or an orthogonal expansion, let's say. So the idea here was, let's assume this function, these functions Rn bar for all m not equal n are all orthogonal. Let's assume that these functions here are all orthogonal. Let's assume all our functions are mean 0, and then also these guys are orthogonal to this and are all orthogonal to this. Okay. And then let's not only assume that, let's also assume that all these functions here have uniform lower bounds. Let's say their norms are all bigger than some delta. Okay. And then if you make all these assumptions, which you might a priori say, well, how am I ever going to verify these? And that's a reasonable claim. But if you make all these assumptions, then you can start to believe that you might be able to do phase retrieval on these subspaces. And why would you believe that? Well, I would take f squared. I would take some other g in my subspace and write a formula for g squared. I'd subtract them. I'd get a expansion like this. This would be an orthogonal expansion. So when I take the L2 norm and square it, I can put all the norms on the coefficients. I assume these are all lower bounded by some delta. So I can lower bound these all by some delta. And then I get a bunch of numbers, just ANs and AM bars and BNs and BM bars. And I manipulate that sum. And eventually I end up at an expression like this, because now I have a chance to because f is written as a series and g is written as a series, maybe I can recover something like this. And it turns out you can do this. You have to pick your candidate for your phase appropriately. It'll turn out to be an appropriate orthogonal projection, but this kind of idea does indeed work. And then, well, that gives me a lower bound on f squared minus g squared in L2, but it will give me, of course, a lower bound on f minus g in L4 by Holder's inequality and the fact that when I do this proof rigorously, I appropriately normalize all my functions. Okay, so this kind of idea, just very naively, will indeed give you an inequality like you want, where the absolute value of f minus absolute value of g in L4 dominates this inf of the distance between f and lambda g. And heuristically, what are we doing here? Well, we're using these products as a way to encode how this subspace sits inside the ambient space, right? Because there's no property of Rn intrinsically that I could put on. I could choose this to be my favorite basis. From a Banach space point of view, it can be extremely nice. No property like that is ever going to tell you that you do stable phase retrieval, because the point of stable phase retrieval is how you sit as a subspace, right? So how does this subspace sit inside of LP, right? And what we're doing here is using the products as a proxy for absolute value, in a sense. So we're saying we're using this comparison of absolute value of F minus absolute value of G, where we're reducing that to products or F squared minus G squared, which allows us to reduce the products of how things work, like how things sit. And this is the idea, because this has nice algebraic properties, right? So the absolute value of F it's not the nice, this is function algebraically, but absolute value of F squared is very nice. And with these orthogonality conditions, you can get one of these bounds at least formally. But there's two problems with this approach. The first is that it necessitates you working in L4, because you want not only an orthonormal sequence, you want products that are orthogonal as well. And products being orthogonal means you need your products to be in L2, which means you need your original functions to be in L4. So this is why L4 norms appear. And the second big problem is, how do you verify all these conditions? And let me briefly tell you how you do that. Well, in the example, we were looking at trigonometric polynomials. So we were looking at the sum from k equals 1 to n of ak e to the 2 pi kx. We assumed that the magnitude of p is not constant, and we assumed that we dilated it by a sufficiently Lacunary number. And how do I verify all the conditions in the last theorem? Well, when I take this expansion, I'll take my basis vectors Rn to just be p of a to the n, right? So this polynomial and this dilates. The fact that I assume absolute value of p is not constant tells me that the absolute value of p is not 1, let's say after appropriately normalizing it. And then when I form dilates of it, I'll get not only that this quantity is non-zero, but it'll be uniformly bounded below, because all these functions are built from dilates. These products I'll get uniform lower bounds on, because again, because absolute value of p is not constant, and I'll look at when Holder is maximized, and Holder is maximized, well, essentially on functions of this form. So again, I can win a delta from this fact that modulus of p is not constant. So I'm turning this qualitative assumption about absolute value of p not being constant into a quantitative assumption by using dilates and all these things. And then the fact that I'm using very sparse dilates gives me non-overlapping of the Fourier supports, not only of the original functions, but on all possible products of them that are relevant in this theorem. Okay, so this guy Rn bar will look like a product of a dilate of this and a dilate of its complex conjugate of something else, and I'll look at the Fourier supports of those, and I'll use some combinatorial type arguments to show that these will always be like non-disjoint sets, and for that reason I can get all these orthogonality conditions. And now the assumption that I have no negative frequencies becomes very relevant, because I don't want any possible cancellations when I do these products, right? So if I had some negative frequencies, they could, in principle, cancel with positive frequencies and then give me non-disjointness on the Fourier side, and hence non-orthogonality on the physical side. All right, so that's morally speaking how this theorem works. Again, here we use Lacunary dilates. You can improve this a lot to witness the lambda p set inequalities. So you can witness the bounds of root in, but I'll skip that. All right, so the next problem is, well, this this procedure, we looked at orthogonal products, and that necessarily meant we had to work in L4 rather than in L2. And most phase retrieval problems are happening in L2, so we want to get rid of this assumption. And how do we do that? Well, let's note a few things. So if E does SPR in L4, then this star 4 property holds, and hence star Q holds for all Q less than 4. But if we also assume that star Q holds for some Q strictly bigger than 4, then by holder, we can deduce a certain inequality, right? So if we make just a very small supplementary condition, which is necessary by Dan's talk, because we could build subspaces where your SPR in L4, and so you satisfy star 4, but you don't satisfy star 4 plus epsilon by Dan's talk. But if you assume such a thing, then by a very simple holder argument, you can get to L2 at a cost, and the cost is that, well, I lose some regularity. I can only control absolute value F minus absolute value G if I dilate it by a gamma, and then I have another factor that scales me to the ball. So this is what I can deduce from such an argument, and this will work for Lacunary Fourier series because all the LP norms are equivalent. And this inequality tells me, well, it tells me that the recovery map that sends absolute value of F to F modulo phase is well defined and holder continuous on the unit ball of L2, right? So the point here is that if I can get Lipschitz SPR in L4 and a little bit extra integrability, then I can get holder continuity of the phase recovery map on the unit ball of L2. And then the question is, well, how do I go from holder to Lipschitz? And we have a nice theorem on this, is that, well, for subspaces of LP and actually any Banach lattice, holder stable phase retrieval is exactly the same thing as Lipschitz stable phase retrieval, which turns out to be quite powerful because you can now exploit many extrapolation arguments and stuff, because I can now free to lose regularity whenever I want, because by this theorem, I can win it all back. Okay, so what I mean more precisely, I mean, well, if the absolute value of F going to F modulo tilde is well defined and continuous on the unit ball of E, then it will necessarily be Lipschitz continuous on the whole of E, of course, with a much bigger constant, a constant that scales like 1 over gamma, but nonetheless is finite. Okay. And to prove this theorem, we identified where instabilities can occur. And this theorem here is I should maybe emphasize, is both for real and complex scalars. And it says that instabilities in phase retrieval problems always happen on orthogonal vectors. So our theorem says that if I take F and G in L2, let's say linearly independent, then I can always find 2 more vectors, F prime and G prime, staying in the span of F and G, where now F prime and G prime are orthogonal, and replacing FG by F prime G prime tightens the SPR inequality, right? So the left-hand side gets smaller when I replace FG by F prime G prime, and the right-hand side gets bigger, okay? And the consequence of this is that when I want to verify that a subspace does SPR, I can, without loss of generality, assume that my functions are, well, first off, normalized, so I can scale the bigger one to have norm 1 and the smaller one to have norm less than or equal to 1. But critically, I can also assume that these are orthogonal vectors. And this is, I can point out here why this is very nice. So what I'm interested here in is an infimum over all possible scalars of F prime minus lambda G prime. But what happens when I assume that F prime and G prime are orthogonal? Well, then I can just, this quantity here doesn't depend on lambda in any way, right? Because I have F prime minus lambda G prime in norm squared is just the norm of F prime squared plus the norm of G prime squared. You have this Pythagoras' theorem, right? And again, because from this normalization, it tells me that that this number here is independent of lambda, and it lies somewhere between 1 and root 2. And not only do I somehow kill any possible phase, which makes complex phase retrieval problems harder, but I also never have any cases where I have to assume that this quantity is small, right? And now heuristically, you can see exactly why Lipschitz implies Holder, because Lipschitz and Holder are different when functions are near infinity, but I scale everything to the ball. That's why I have this scaling factor here that pops up. It scales everything to the ball. And Holder and Lipschitz are different near zero, but I don't have to care about that because I can always assume that the left-hand side of my phase retrieval inequality is uniformly away from zero. Okay, so this is why Holder SPR implies Lipschitz. And what's cool about this result is that it actually works in any Banach lattice as long as you understand what orthogonal means. And the reason is because this first process of orthogonalization keeps everything in the span. So it's a two-dimensional process. And I can renorm any space to be like two-dimensional space to be Hilbert and do that process there. And from the proof, I can actually establish this inequality on the pointwise scale. So instead of taking norm of both sides, I can take absolute value of both sides and establish that. So as long as you assume orthogonality means that, you know, within factors of root 2, this quantity is just norm of f prime squared plus norm of g prime squared square rooted, this theorem will actually work in any Banach lattice. All right, so I think that's all the time I have for today. So I'll just start listing some other results we were able to prove. And the first thing I'll note is that although this talk was about LP, many of the results hold in general Banach lattices. We were able to prove, for example, that every subspace of an order continuous Banach lattice has a further, sorry, I stated this wrong. Any subspace of an order continuous Banach lattice that does not have an almost disjoint sequence, so it has this star property, will have a further subspace doing stable phase retrieval. So that says that if I have any subspace without almost disjoint sequences, a further subspace will have no almost disjoint pairs at all. We were able to prove that C of K admits an infinite dimensional SPR subspace if and only if the Cantor-Benedictson derivative is infinite. We were able to prove that every Banach space embeds isometrically into C01 in an SPR way. We were able to prove L infinity embeds into L infinity in an SPR way. You can prove no subspace of little LP when P is finite can be SPR and infinite dimensional. And then we studied some stability properties. So SPR subspaces are open in the Hausdorff metric. We were able to prove, build some nonlinear subsets that are not subspaces, but nonetheless they are phase invariant and they are relevant in certain applications and do SPR, and some other results that if you want to read, you can. So anyway, thank you very much for having me.
Okay, thank you so much. That was a very nice talk. Are there any questions or comments?
I do have a question.
Yeah.
I want to go back to two theorems, after which, just after which, the property star appeared.
Okay.
And so they are considering closed subspaces.
Right. Okay. Yeah.
Is it true for say not entirely closed, like subspaces which are operator ranges, which could be also useful, I think?
Well, I don't know the answer to that question in the language of the star property, but I do know the answer in SPR, and SPR passes the closure. This is something that's true. So if you have a subspace where you can verify the SPR inequality, then the closure of that subspace, it'll also be true. For almost disjoint sequences, I'd have to think for a few minutes unless somebody knows the answer. But for this talk, I was, I guess, sloppy in whether I said closed or not.
But my question, is the theorem true for a non-necessarily closed subspace?
Yeah, that's what I was saying. I don't know if this theorem is true, but what I'm saying is all of the other results we proved, it doesn't matter if you're closed or not, because you can pass to the closure, but I'm not sure about this particular theorem.
Thank you.
And well, I also promised that I would explain why this is true. And for some people who know this, you can look at, you have this result of in lambda p set theory, or also Rosenthal's generalization. Well, I guess not generalization, because I think he probably proved it first. If p is less than 2, then you don't, and you have this star property, then you embed into LP plus epsilon. And that's true when p is bigger than 2. And so if you know, and what I was explaining is that you have these extrapolation arguments now that you can use. They don't work in this case because you only get an isomorphic embedding. It doesn't preserve any lattice structure, so you can't use them, but at least heuristically speaking, that's why these are true, because if you have star p, you kind of have star p plus epsilon in this case, but we can't use those arguments directly, but that's maybe formally why this works.
Okay, any others?
Mitch, maybe the answer is obvious, I'm not sure. What does it mean to say that in LP for P different from 2, a subspace has stable phase retreatment after applying a space isometry?
So I can give you a simple, well, I don't know if I can give you the full answer, but you can say this at least. If you have a subspace of LP that has no almost disjoint sequence, then I can find a further I can find an isomorphic subspace that we can do SPR. So I mean, if you want, so one thing we were interested in is classifying up to Banach space isomorphism all subspaces of a Banach lattice that do stable phase retrieval. And for every example so far, up to Banach space isomorphism, the set of subspaces that can be embedded into your space that to not have an almost disjoint sequence are the same that can be embedded in an SPR way. I don't know if this answers your question. You can restate it if you want, but
Oh, I was asking about isometries because they preserve the disjointness.
Right. So isometries in the real case are helpful to us in the real scalar case, right? In the complex case, troubles will run, but existence of SPR subspaces can be deduced from the almost disjoint pair characterization, and then just classical results on isometric embeddings into your spaces. Because, you know, let's say when p is bigger than, or p is less than 2, you can embed LQ for appropriate Q and capital LQ, Q tables and whatnot. And these automatically, no matter what the embedding is, as long as it's isometric, it will do stable phase retrieval just by 2-dimensional Banach space arguments. The isometric theory is very useful for us. I don't know if I have an answer to your question, but it is a way to build these subspaces.
Okay, yeah, thanks.
For other variables like Gaussians and Q stables, you can even prove more that anytime you can put them inside an RI space, they necessarily, like isometrically, they necessarily have to do SPR just by isometric arguments. So Lorentz spaces would also work.
Okay, I think that's about it. Any others? No. Thank you so much for a very nice talk. Really appreciate it. And so let's stop here.